Hey, so this is going to be molecular geometry, right? We've been, or started kind of drawing the structures, Lewis structures for molecules. And we said that we want to do that so that we can determine the molecular geometry. And from there, we can determine polarities of molecules. And from there, some physical and chemical physical properties mainly. I'm going to share my screen. Please make sure that you have your periodic table and even maybe more importantly, your molecular geometry chart that I had asked you to print the other day and bring into class. Please pause right now and get that if you do not have it. Okay, thanks. All right. And once again, we are going to discuss molecular geometry. You need to write down everything I write down. Okay. So do not be a passive listener, but be an active listener. And as you write, you need to think about what you're writing. So do not just write it, but think about it. Think about what the words mean, such as molecular geometry. We're obviously talking about these shapes, the geometric shapes that molecules take, okay? There is a theory called the Vesper Theory. You need to write this down. It's called the valence. We know what that is. Shell, the outer shell. Electrons, okay, electrons on the outer shell. Repulsion, okay, so the electrons on the outer shell are going to repel each other. That is the theory, okay? Such that the shape of a molecule minimizes those repulsions. Molecular shapes minimize electron repulsions, all right? Remember that these are, we're showing how bonds are shared. Bonds, they're sharing electrons. There are other electrons around the atoms and they repel each other. So the shape that a molecule will take will be that shape that minimizes the electron repulsions. Let's go ahead and get started by looking at an example. Let's do carbon dioxide. All right, carbon dioxide. Let's take the same steps in drawing the Lewis structure. Carbon donates 4 electrons. We have 2 oxygens, each that donates 6 electrons. That gives us a total of 12 plus 4 is 16 electrons available for bonding. We will now, we will now arrange our atoms. Carbon loves to be in the center, and we will put the oxygens around like such. We will connect with a line, which is a shared pair of electrons. That is 2 electrons. Minus 2 is 14. Connect these. Minus 2 is 12. Let's pick an outer atom. I'll pick this oxygen. And let's satisfy the octet for that oxygen. We just use 6. 6 remain. Let's go to the other outer atom. Let's satisfy his octet if we can. Okay, we just use 6 electrons. That leaves us with no more electrons remaining. Okay, this oxygen here has 2, 4, 6, 8 electrons around it. We have satisfied the octet. This oxygen here has 8 electrons around it. We have satisfied the octet. Do not forget about carbon. Carbon currently only has 4. We have not satisfied the octet. So what we need to do is we can't add any more electrons. We don't have any more. We need to start moving things around. We know we're not finished because carbon is not because carbon only has 4, and the goal is to satisfy the octets, with the exception of hydrogen, who gets 2. So let's let the outer oxygen, let's take away one of his pairs and share them. He still has 8. This carbon now has 2, 4, 6, and this oxygen still has 8. So because carbon in the center only has 6, we need to have someone else share with him. So let's get rid of those lone pair. And he still has 8, but now carbon in the center has 2, 4, 6, 8, and so does oxygen. So this is good. And there is our Lewis structure. Now let's determine the molecular geometry, okay? You need to be writing all of this down. And you need to be thinking about what's going on. And if you don't understand it, you need to put a star on your piece of paper, and you need to ask, Ms. Murphy, in the first example, why did you do this? Okay, I'm now going to count my domains. All right, I need to determine the molecular geometry. All right, so let's look at our molecular geometry chart. Please pull out your chart. You should have a printed copy. And notice that I see the word molecular geometry right here, all right? I also see next to that, I see electron geometry. So let's talk about what the difference is. The electron geometry is determined by the number of domains. And you should be writing this down. The molecular geometry is determined by within those domains how many are bonding, and I'll go over this in a minute, and how many are non-bonding. Number bonding versus number, oops, that's supposed to say non-bonding versus number non-bonding, okay? So our electron geometry is broad, whereas our molecular geometry is more specific. And Ms. Murphy is more concerned with the molecular geometries, okay, because this tells us the actual shape of the molecule itself, okay, and all the way down. Ooh, that's messy, I just looked up. So we will be concerned with the molecular geometries, okay? So when we talk about the electron geometry, we've got to find that first. It says, what did I write down? I wrote number of domains, okay. Let's go back to our notes. And on your notes, let's write number domains over on the side so we understand what we mean. And this is strictly around the central atom, okay? Or the atom under discussion. All right, well, a lone pair, 2 dots, is 1 domain. All right. One shared pair, a single bond, a double bond, and or a triple bond are also 1 domain each, okay? So let's look at what Ms. Murphy's talking about. Let's go back to our first example, example number 1. You should have all of this written down, okay? And I want you to let's look at our carbon dioxide Lewis structure. Let's look at our central atom, and let's look at the number of domains around that central atom. Well, this is easy. It looks like there are 2, 1 domain, 2 domains. So for my molecular geometry, I have 2 domains. It looks like they're both bonding because they're lines. And there are 0 non-bonding because there are no lone pairs. So let's go to our molecular geometry chart. And let's look at this electron groups. That's actually the number of domains, right? It's the same way to say, different ways to say the same thing. What we just had was carbon dioxide, who had 2 domains. Carbon dioxide had 2 domains. They were both bonding, and we had 0 lone pairs. So our molecular geometry, remember that's the one I'm concerned with, our more specific geometry is linear. That makes sense, because in order to minimize all of those electrons, why are you not seeing all my things? We would look at the first row. Why are you not seeing it? Is there a problem with the Wi-Fi? You're not seeing everything I have on the screen. But there we go. 2 electron groups, both of which are bonding. We have 0 lone pairs. We're concerned with the molecular geometry. That is the orientation that will minimize repulsions for any molecule that has 2 bonding and 0 non-bonding. So we will call the carbon dioxide molecular geometry linear. That makes sense. It looks like a line, right? Let's look at another example. All right, let's look at BH3, boron trihydride. Let's add up our electrons. There are 3 hydrogens, each donates 1. That's a total of 6 electrons available for bonding. We'll put boron in the center. We'll spread out the hydrogens for now. We will connect 2, 4, 6. I've just used all of my electrons. None remain. Oh, why is it lagging on me? Come on, draw my lines. I'm gonna have to make this video again. I have so much to do. I've already made this video once and it messed up. This isn't gonna work. Goodness gracious, are you kidding me? This Murphy has so much to do. I am sharing my screen. You should not do this before it updated. Okay, I'm not gonna rewind, y'all. I'm sorry about that. Okay, we're back. So, right, what I see is I have used all 6 of my electrons. All right, let's look at the octet rule. Remember, hydrogen has 2, that's perfect. 2 for hydrogen, 2 for hydrogen. And notice that boron here has 6. Well, that is less than 8, obviously, okay? And that is okay. It's called a sub-octet, which means you have less than 8 around the central atom. This is often occurs with the 2 B elements, boron, and beryllium, boron and beryllium. Okay, let's look at the arrangement that this boron trihydride molecule would take in order to minimize repulsions. What do we call its shape? Well, the molecular geometry, rather. We've got, it looks like we have 3 domains, and with those domains, all are bonding. Okay, so we have 3 bonding domains and 0 lone pairs or non-bonding. So let's look at our molecular geometry chart. And let's go to where we have 3 domains, all right? And we see that we have that twice. But in ours, we have 3 that are bonding and 0 lone pairs. So we will take a trigonal planar arrangement. And what you'll see is we will look like a triangle and it will exist on one plane. So Ms. Murphy's going to have you go back to your example. Oh, and there we go. We drew it correctly. And this is trigonal planar. Now, hopefully you followed along. You did not just write it down. You thought about it. And if something doesn't make sense, you've written a question mark to yourself, because I would love to help you work through something that doesn't make sense. Let's do another one. Let's do H2S. Okay. Come on. All right, let's count our electrons available for bonding. I've got 2 hydrogens, each donates 1. And I've got 1 sulfur, which will donate, oops, that's supposed to be a 6, not an S, donate 6. It gives me 8 electrons. Remember, hydrogen is never in the center, so I'll put sulfur there. And we'll just go ahead and see how this works for now. Oops, come on. Why all this lagging? It's driving me crazy. So put the S in the center, there you go. Put the hydrogens around the side. Let's connect 2, 4. So I have 4 electrons left over. Hydrogen here has 2, that's perfect. Hydrogen here has 2, that's perfect. Therefore, the remaining leftover 4 electrons must get placed on the central atom. So I just used 4 and none are left over. Sulfur here has 8. So that's pretty good. It was that simple. Let's get our molecular geometry. Okay. And let's look at the number of domains. 1, 2, 3, 4. So I have 4 domains. Within those domains, I have 2 are bonding and 1 is non-bonding. Oops, no, 2 are non-bonding. So let's go see what that shape would be in order to minimize the repulsions. What shape would this molecule take? Well, let's see, we had 4 domains. So we could take 3 different shapes with 4 domains. However, for us, we had 2 were bonding and 2 were non-bonding. So this molecule will be bent and it will look like this. So we're going to take what we drew and we're going to redraw it in a bent geometry because it will really be S with the H's bent down. Oh, come on. There we go. With the H's bent down and 2 lone pairs on top. It is bent. Okay. The presence of these lone pairs, they are very negatively charged. And they are big, like big negative Mickey Mouse ears. And they push these bonds down in an effort to minimize repulsions. Remember the valence shell electron pair repulsion theory. Okay, let us do one more, I guess. Let's do NO2. No, we just did that one. Let's do NH3. That's easy. N offers up 5. We have 3 hydrogens, each donates 1. That gives us 8 electrons available for bonding. Let's put nitrogen here, hydrogen, hydrogen, hydrogen. Let's connect 2, 4, 6. That gives us 2 electrons remaining. Well, hydrogen here is good with 2, 2, and 2. So the remaining electrons must go on the central atom. Let's get our molecular geometry. All right. And in that molecular geometry, we have, let's count our domains. 1, 2, 3, 4. 4 domains. 3 are bonding. 1 is a lone pair. All right, so let's go look at our molecular geometry chart. We have the 4 domains. So we know that we're within here, right? We're either here, here, or here. We had 3 bonding, 1 non-bonding. That makes us trigonal pyramidal. And we will look like this. And our lone pairs will be sitting on top. And we will be bent down. So I'm going to redraw this such that my lone pairs are here and these angles are somewhat bent down. And that is trigonal pyramidal. Hopefully this has helped you not only determine the molecular geometry, but to also help you actually draw those structures, okay? I hope that you wrote all of our examples down. How many did we have? We had 2, then we had 3, then we had 4, okay? And please write down any questions that you may have and bring them to class, all right? See ya.